Hello everyone, welcome to CYBR601 Introduction to Cybernetic Modeling and Simulation Learning Activity 13 for Model-Based Systems Engineering. So what is model-based systems engineering? Well, when you look at it from a high level, model-based systems engineering is focused around taking components, linking them up into models that we create. And of course, you've heard this again and again, models, right? Models form the basis of this course for the purposes of simulation. But in this particular case, model-based systems engineering has a different flavor. It's more architecturally driven. It's more systems engineering driven. And what I mean by systems engineering is actually it's more life cycle focused. But we'll get into the details of what that means. But you can see over here the kind of the technical detail. The idea of MBSE supports complex systems development through the creation of or through the illustration and development of requirements, through the development of designs and system design patterns. We go on through the whole process of not just analysis and verification, although that's definitely a part of it. This is kind of the INCOSE, what I'd say the INCOSE, which is a software engineering association or systems engineering association. I think International Organization for Systems Engineering is essentially what that is. And I think International Council on Systems Engineering. So that's what INCOSE stands for. And so this is more of kind of like a formalized definition on your left in terms of when they say analysis, verification, validation. But there's a lot more to that systems engineering life cycle, as we'll see as we move along. But essentially, MBSE it differentiates itself from other more traditional document-centric engineering routes. And so, traditionally, what you'll do is, as an example, what you might do is you might say, "Hey, well, I'm gonna create a Word document, and then I'm gonna formalize all my requirements in a Word document. I'm gonna formalize all my planning in a project plan, another document. I'm going to formalize my architectures within a document." And what happens is it's not that MBSC doesn't use documents. It's just model centric. And the idea is that models are emphasized over documents. And so in the sense that traditional engineering uses your document centric engineering, and what we mean by that is it emphasizes that. It doesn't necessarily mean that it's a document only driven process or a model only driven process. They both share, model based shares with document centric, and document centric engineering shares with model. It's just that they have their emphases, if that makes more sense. So the idea is MBSE emphasizes model based systems or model centric approach, which means it's more visual, and it can be more visual, I should say, versus a document-centric approach would tend to have a tendency to be more textual. So anyway, that gives you high level, and what we'll do now is see what we've got next here. If I can get this, here we go. So an example of MBSE in terms of components that we develop at a lower level, and we've talked, I would say that up to this point for modeling and simulation techniques that we've run through, right? Numerical, discrete event simulation, numerical simulation, system dynamics. You've gotten a flavor for the component level framework up to this point, because we've through the code through Python, you've seen the individual components. But of course, if we pull that up a level and we say, hey, we're going to use discrete event simulation within a system, then we get into the MBSE world. So there's kind of this natural progression of, okay, now that you've seen all these different modeling and simulation techniques, what is all this talk about model-based systems engineering, or MBSE? If you're interested in learning more, and Lockheed Martin on the right here has a very good, there's a link, a reference to that for Introduction to Model-Based Systems Engineering, and that was at an INCOSE chapter meeting. But Lockheed Martin had put that together, and so I pulled this graphic from their presentation because it actually sums up really well. It's a good example of what is MBSE in real life at a high level. Well, MBSE doesn't focus on all of the systems engineering that occurs. It focuses on or when I say systems engineering, in this case, this focuses on the system models as they relate to the operational models. It's the integration between the two, what we develop on the system side and how it gets fielded out on the operational side. And what happens in the middle is MBSE. The components, that's a much lower level. So when you look at what MBSE is, it's a very high level framework. But it also is driven by this concept of system life cycles, which is systems engineering is the process of managing engineering products through a development from conception to production and post-production, which would be considered operations and support. And because of that emphasis on that end-to-end, that ideation to operationalization, MBSE because it has that purview and that perspective that goes not just to how do I deploy something to production, but it goes beyond that, and focuses on operationalization as well and all the mechanics that happen there. It makes MBSE very popular, especially in the military world, as well as the space world. The space industry is big on MBSE. Other industries are very slow to catch up. I would say that your automotive development, high-end manufacturing will have flavors of MBSE, but NASA, SpaceX, Tesla, I'm trying to think of some other Hitachi, Samsung, they're probably going to be using MBSE quite a bit, just because it tends to favor those very large organizations. Not that smaller organizations can't use it, but there is this tendency for very high-end, heavy industry. When I say heavy industry, heavy industries, those kind of Boeings of the world, Hitachis of the world, those being considered heavy industries are going to be really big into MBSE. Okay, so what are the components of MBSE? So if you go and look this up, you're going to find a lot of different opinions on what are the main components or main drivers that underlie model-based systems engineering. Well, one of those, no matter what model you go to look at for model-based systems engineering, every one of them is going to have a model centricity to it. So model-centric is number one. These other three are kind of, to a certain extent, a conglomeration of what I feel is what MBSE is. These are the major components. Well, so I would say that you of course have model centricity, you have requirements, and that is its own slew of, we can spend a lot of time just on requirements. Then another slide on life cycles and systems engineering, and I do teach a whole course in just systems engineering, which you will get a graduate level version of that in our next course, which we'll kind of do a follow-up in CYBR603. We'll do a follow-up to systems engineering, and we'll start to get into what that looks like Nothing to worry about right now, but something to be on the lookout for here in a few weeks. And then lastly, systems thinking. The idea, and I think that's one of the hallmarks of MBSE is forcing an engineer to be more broad in their thinking, and more connected into um, the system that they're developing, and not just in the component level, but how does that component interact across a broad spectrum, or how does it fit within the broader, spectrum of the ecosystem rather that component exists within. So that's definitely a really huge, important piece of MBSE. Okay, so one of the big reasons why MBSC has gotten so popular is because of these three things on the left. It quite simply, as time has progressed, MBSC as a discipline has been around for some time, and you can see MBSC in NASA very been around for a bit, and I would say that the increase in digitalization, right, the internet, the increase in content creation, the increasing digitalization of everything that we do, right, pictures, um, to blogs, to videos, to TikTok, to social media, to LinkedIn. I mean, we're just so there's that cyberspace and metaverse, right? These just when you look at it and what that spawns off in terms of what it creates is a craving for digitalization, digital content, and the spread of digital information, right? I mean, digitizing information, but then making it more freely accessible and more publicly available and in more fidelity. It takes a lot of bandwidth. So when you're trying to interconnect devices, there's more bandwidth. When you're trying to secure those, right, cyber operations, when you're trying to secure those devices, there's more bandwidth. Machine learning and artificial intelligence, there's more bandwidth. Autonomous systems, right? There's this idea of more intelligent, disconnected but bodied robotic entities. That autonomous systems. That's all things drones. That's all things full self-driving cars, which is not far off. That's also autonomous unbodied systems, which would be your chatbots, Chat GPT, things like that. So these are things that all it's this drive towards in more technological digitalization is why MBSE is gaining so much traction. So, what does NASA have to say about it? Well, NASA has really been at the forefront for MBSE and has been a big advocate. They make MBSE it's their mascot. If there was a methodology that could be turned into an animal, then MBSE would be it would be it. They actually have a patch for MBSE at NASA, but they use it. It's a core part of their ethos at NASA. So of all the references, and you'll be doing you have a healthy dose of reading this week that you'll be getting into, but and it's NASA's take on it. So you've gone through over the past few weeks and gotten a DoD spin on things, and it's definitely important to them. But you also will get one of my more favorite ones is the NASA brief. So the NASA uh, um, um, the NASA PDF that you're going to get a little bit later. And I provide a link for it, so you'll get it. It's free, so you get a copy of it. But yeah, that'll be a good read. It actually lays out a lot of MBSC, but a simulation. Just I would say simulation frameworks in general. So which would be in support having MBSC to support it. But yeah, so we'll definitely have some more to talk about that down the road. So first up in our component view of MBSE is model centricity, or this model centric view. We kind of juxtapose that to document centric, but model centric. It's just an architectural representation. It doesn't. It's just like we've said before, right? It's it a model is something that represents a recreation of reality, and that's no different for MBSE. And But what we do in MBSE world is there's this fine balance between um, what can how much can I recreate from a model perspective. I don't want to make it too simple. I can get away with simple and other things like numerical simulations. I can get away with a very simple point model, and that works great. But for model-based systems engineering, I really can't get away from something that simple. So you have to balance out detail with you want some detail so that there's some structure that can be applied to it, um, and um, and honestly understood by a broad set of people, because in the MBSE world, you'll have business people looking at your architectures, and so you have to find that balance between too much detail, and having too much, or having not enough. Regardless, that bottom bullet is absolutely 100% correct. Yeah, models should sufficiently represent the system, and the system should confirm the models. So, as an example on the right, a very simple one. It's kind of hard to read if you're going to try to zoom in on those little guys. But high level, this is what I'm looking for: is that you've got on the left, you've got your environment for, in this case, it's your business environment, and this is just an example doors environment, it's a business model, and they got customers, safety, human factors, requirements, supplier specifications, and so requirements as well, and all of these get fed into a model environment, which would be our MBSE. And the model environment uses what's called SysML. And you're probably wondering, what is SysML? So that leads us to our next thing, which is system modeling language. So before we head on over to requirements, we'll talk a little bit about what this SysML is. So it's called system modeling language, and it's a general purpose language used for diagramming out systems. And and on the right hand side, those are all system modeling language examples: parametric, activity, use case, sequence. These are all diagrams that are used by in SysML. And what's the idea behind SysML is these are stencil sets. When I say stencils, I mean like they're a particular stencil format in terms of the visualization tool, but they support what's called a system of systems view, and the idea is that the visual modeling language that you use to create the diagrams, they have an ability that they're built in such a way, and they have a taxonomy that supports systems thinking. Actually, that's probably a better way to put it, instead of just systems of systems, but systems thinking. And you'll probably notice, if you have any experience with diagramming, especially as an architect, you'll probably notice right off the bat that these look like UML diagrams, and which stands for Unified Modeling Language. And the reason for that is because they are absolutely very much related. Actually, SysML is a subset within Unified Modeling Language. SysML is a portion. And there's a small portion that is not part of UML. So you'll see that in the Venn diagram on the right. But you'll see that UML supports all kinds of stuff: communication diagram, timing, interaction, composite, component deployment, object, and profile. And there's very similar on SysML, sequence, activity, state machine, use case, a couple other like block definition, internal block diagram. They look a little different. But overall, still in very much SysML is very much within the UML wheelhouse. If you're interested in learning more about this, you can look at, there's a link on the left here. You can go check that out, and that'll pretty much get you a little bit more detail. Okay, so requirements. So let's talk about requirements. So on the left, we've got business requirements, which are your overall high level stakeholders. Your audience is usually your chief exec, your C-level people, right? Your CXOs within the organization, and they'll usually there's a business objective, of course, that supports that business requirement, and that's usually your top level, high level requirement. Then you've got user requirements, which is user interactions. It could be, for example, the business creates product has users, those users interact with your product, and you need to understand what that point of view is. So there's a requirement, point of view rather, and so there's a requirement from that perspective that is very important as well. System is the technical, right? It's the interstitial piece of it. That's the system requirements are what bind. It's the product, right? It's whatever it is. It's not, well. Let me rephrase that. It's not just the product, but it's the whole thing. It's the user, the product, the business, everything all together. And you can really slim or reduce, basically, essentially. It doesn't matter if it's the military or if it's Microsoft. You can really essentially reduce any of these concepts down to business product users, or business with system being the thing that glues everything together. And yeah, so this can get pretty complicated, especially when you talk about really big organizations. But from a system perspective, it's broken down into two different areas. There's functional, which is what the system does, and then there's non-functional, which is how well the system does it. So I've broken out on the right-hand side the difference between functional and non-functional. And so there's just two examples. So functional, when we say what the system does, we're talking about, as an example, if I'm building a new software system, and part of that software system, I put a functional requirement in that says the system needs to send a confirmation email when a new user creates an account. So in other words, when I go to create a new account for whatever it is that I'm building, if I'm building a new LinkedIn, then when someone creates a new user account, it should send an email confirmation back. That's a functional requirement. Now, if I'm building a website on the flip side for this application, and then whatever it is, a non-functional requirement is how well the system does it. And so in this case, it's a measurement. So when you think of it this way, that kind of helps to simplify the difference between functional and non-functional. But the example I put here is the system should be able to handle 20 million users without performance deterioration. So, well, that means that that's a measurement, which is a non-functional. It's a performance. Anything that's a performative measurement usually is going to be something that is how well the system does it, as the in quotes, and that would be a non-functional requirement. Okay. So next up, we've got life cycles. So life cycles, second to last here. So when we talk about life cycles, we're really talking about systems engineering. And I'm really glossing over quite a bit. And we're going to get we're going to get a deeper dive into the systems engineering process in CYBR 603. But for us right now, just know that systems engineering, from a life cycles perspective, we're talking about the ideation to, and these buckets can change depending on the life cycle. But we're talking about the ideation to warranty or post-production operations. So it's project life cycles and operational life cycles, or what we'd call PLCs and OLCs. And what I'm showing here is just high level, because each one of these buckets change depending on the method. And that's where systems engineering comes into play too, is understanding the pros and cons of the different methodologies. So for example, if I said, hey, I want you to compare and contrast a systems engineering lifecycle, waterfall versus agile. Great, those are two popular ones. But if I said, hey, agile is not going to work for us, what others are there? Well, you've got Kanban. That's another system. You also have test-driven development strategies, or TDD. You have pairwise programming, which is more on the software development side. You have Scrum. You have spiral methods. You have, there's just, you name it, there's quite a few different methods. And I'm just scratching the surface. There's a lot of others that we could name off. But yeah, so we do actually teach. There is a whole course on just systems engineering that we have here, and we'll be spending a little bit of time on that, and yeah, it'll be good. So I'm gonna put a pin in this one for right now, because we're gonna circle back on this in a few weeks. But just know that when we're talking about model-based systems engineering on the life cycles, we're really talking about we're really talking about the domains that manage the pipeline of the development through from ideation to operationalization, and all the steps in between. All right. So part one, this kind of wraps up the components of model-based systems engineering. So systems thinking part one, I want to make a differentiation between systems thinking and design thinking. Both very, very important. Systems thinking has this tendency to be thinking very broadly in layers, and the idea is that you have a much broader, not just organizational view, but intra-organizational view, but also an extra-organizational view. So things that are happening inside, but also things that are happening outside. So it's that ecosystem level perspective, and having that understanding that not all the relationships, but at least having some understanding of most of the relationships, or that how things are impacted, at least notionally at a high level, between between entities, or between models within a world simulation, or models between actual physical reality. So that's definitely something to be thinking about. Okay. So on the design thinking side, it's a very different view of the world, right? The questions that are asked, it's not so much about connectivity, which is what systems thinking is focused on, but on design thinking, it's about where there's optimal synergies between what you see here: desirability, viability, and feasibility, and bringing those all together. Now, I think when you bring these together, right, systems design thinking, you get a nice pairing, because you have to do the systems networking part of it, systems thinking and being able to network things, but also you have to bring in design thinking. And hence why, to a certain extent, you've got the master's program, Master of Science in Integrated Systems Design and Dynamics. So there's this design and dynamics really is a big core of what it is that kind of, to a certain extent, what you're seeing here. Okay, so part two. So what does it take to be a systems thinker? Well, It just like it's some little visuals here to kind of help you understand. Um, people that get into uh, this work have a good feeling for. Of course, you can't know all the individual connections, but having a feel for interconnectedness or the layering within the organization and the major touch points, that's pretty important. And that's definitely one of the tools for a system thinker. Another one is being able to think of like linear versus circular or a hybrid of both in terms of is seeing things for not just linear systems but also complex systems. That's definitely in our wheelhouse. Silos versus emergence. Emergence is very much something that we want to be on the lookout for. Emergence is the concept that something evolves from a product that it wasn't originally specced out. So in other words, you build a product and then the consumer or the user uses the product in a different way that you hadn't intended it to be used. That's called emergence. And in other words, it's one of those things where people find a way to new capabilities out of something that wasn't originally thought of. On the lower left hand, parts of the whole, that kind of makes sense, right? We know that, from that systems thinking, having a whole view of something is definitely within what we're trying to build out of this program, leaders for that we end up um, building within the program. So the ISD program rather. So then analysis and synthesis, and those are both very important. And then isolation and relationships, again, back to that connectivity, but looking at it from a slightly different perspective. Instead of disconnection, we call it isolation, and then interconnectedness in relationships. There's a kind of a social ramification, whereas on the upper left, it's kind of more of a physical hardware slash technical kind of connection, whereas in the lower right, you're looking at more of a social kind of connection. So yeah, but these are definitely all little tools, little tidbits, and things to be keeping in mind as a systems thinker. Okay, so you'll probably that wraps up the major components of MBSE, which gets us to the MBSE simulation architecture. And you will notice right off the bat, and you probably asked yourself this question early on, like, why is there a simulation anywhere in our future? And the answer is not really. There are MBSE simulation tools. They absolutely do exist, but MBSE by itself is not really a simulation framework. It's a modeling framework, but it's not a simulation framework. So the engine behind it, it's more of a methodology. They can have multiple different engines, and it can be different routes, different methods, different. I mean, and so the really, it's kind of one of those things that when you think of MBSE, um, you you kind of want to make sure that you understand that it's a methodology and a framework for modeling systems engineering processes. Okay, so moving on to the lab. So we're gonna do things a little differently. Our follow along, we're gonna do an Unreal Advanced simulation, and it's gonna be a simple one, but it's gonna be complicated for what it is that we've done to this point because when you get into the Unreal world, everything is complicated. But we'll do a quick follow along. You get some familiarity, high level with a tool called Blueprints, and then on the UTry, I'm gonna have you create a sysml diagram using UML, Unified Modeling Language, and using an online tool. You don't have to download a tool. You don't need Visio or you don't need to use PowerPoint. Just an online tool. This www.diagrams.net. I'll give you the high level, but then what I'll do is talk you through the next steps, which is creating an activity diagram. So labs for this week, M&S Lab 6, week 6 labs. That should actually not say follow along for SD simulation. That should actually say follow along for Unreal simulation. So that's kind of, yeah. So, and then the next is creating an abstract balancing loop. That was last week. Apologies. That should be adjusted. But anyway, for the U try, we're actually going to create. Let's see if I think I've got it. Yes, I'll talk about that next. But I pulled down a Netflix business model, and for the U try lab, you will be creating not an abstract balancing loop because you did that already. But in the U try lab for this week, you're going to be creating an activity diagram using the diagrams.net online editor to create a activity diagram that takes into account Netflix's business model. So that's what you're gonna do. And as you do that, there's a couple questions I want you to ask yourself. What are you trying to emphasize with your activity diagram? Because everyone's gonna have a little different perspective on that. And then when using MBSE, in this case, who is your audience? Okay. So before I talk through the lab requirements for the Netflix thing here in just a second, just know that readings for this week, you have one reading, which is Technology Area 11. This is Modeling, Simulation, Information Technology, and Processing Roadmap. And it's put out by the National Aeronautics and Space Administration. And here is the link right here, that PDF. It's a great read. I highly recommend it, also because it may show up on a quiz. All right. So on the U-Try lab, I'm going to have you create a UML activity diagram of the Netflix business model. And here's a copy that you can leverage, so feel free to pause it. But this gives you key partners, activities, value props. So this is a perfect activity model. Right now, it's just kind of high level business canvas or model canvas, which is fine. It keeps things easy and it's great at a high level. But if we need to build something a little bit more detailed, we'd need to switch over to UML and create an activity diagram, which is what I want you to do here. I want you to create an activity diagram of this. And if you have questions around an activity diagram, I will bring up an example here in just a second, and then we will talk to the final project just for a second. Okay, so the best way to do this is just look on the internet, activity diagram example, and then type in UML, and then go to images. And you can find some different examples, you'll find a whole bunch of different things you can take some inspiration from. Essentially what you're going to do is you're going to use diagram.net to create this an activity diagram like this. So this is a great activity for the activity diagram. So yeah, there you go. Okay, so I'll actually cover more of this in the lab, but this is the general gist of what we're trying to do. Okay, so let's switching off and wrapping this lecture up. So from a final project perspective, one of the things that I need, or rather is suggested, and let me go ahead and get this pulled up here. Actually, let me just grab the template. Okay, so now that I got this up, let's talk through this. So you're gonna, I've already gone through some of this early on, but again, let's just run through and just make sure that everyone's refreshed on this. So you'll compare and contrast. You'll put your name. Here's your title. CYBR601, and then your professors, that's fine. And then 150 to 200 word abstract. And I remember talking last time, kind of work in the middle, work your way out. So your middle, and you kind of starting with your literature review, getting kind of a feel for what it is you're trying to do on your research goals and what you're trying to look for, and then open it up from there. So let's talk through the next steps. So as you kind of get a feel for what it is you're writing, and you're starting to build the introduction out, and then you're starting to build out like your background research and what past research is telling you. Then you can start to go into what's called after you get this, limitations. So when we talk about limitations, and these are kind of the last two things I wanted to talk about, which is limitations and conclusions. So limitations are going to be what was a weakness in the research? What is it that from a literature review? So in other words, the background. What did you notice that was missing as it related to what it was that you're comparing and contrasting? So was there a contrasting method that was missing? Was there a different way to do it? Was there another simulation architecture that would do something differently or better? That's something that actually leads into the conclusions. So when you start to get into this part, you can say that there's some questions here to kind of get you started. Why was it important? What did the research find out? What were the unexpected outcomes? These are all things that you'll want to talk about in your conclusion. I would strive to one of the things that a conclusion, especially towards the end, a conclusion could get tough to develop when you're talking about how do you close your paper out, right? I mean, that always can be like, what are my famous last words? What are my thought provoking? Well, what I find that helps is go back to the introduction on your conclusions as you start to write through this. Go back to the introduction, go back to your research goals, go back to your background, and start taking a couple sentences and reframing it as a conclusion for your last paragraph. Take your reader and give them a quick reminder of, this is what we found in the introduction. This is what our research goals were. This is what our background and research and theories were. And then this is what our limitations. These were the things that we found that were off. These are the things that we could not test because, or we could not validate because it didn't show up in the literature, right? And then you discuss how that is an opportunity for the future, right? An opportunity, if there's a gap in the research, then that's an area for future research. And you illustrate that, say it. Just, go out there and tell people, this is where I think, this is why I think our research is important, but I also think this is why it should be continued. So anyway, I just wanted to give a little bit more extra information on this. I don't think I got any more to go for there for the paper. So with that said, that's all I've got for this week's lecture. I will be handing the reins over to Dr. Jackson. He's going to be talking to you about control systems, and I've seen what he's got. I'm very excited for you to be picking up some information from him. He's got phenomenal insight into a tremendous background in industrial engineering as well as materials engineering and materials science. He's mechanical engineering by trade, but he has just a fantastic background to be able to take what we've learned, but then give you a perspective of how do you take modeling and how does modeling and simulation techniques and how are they applied in an industrial setting? So what better what there's no better way, rather, that's what I was trying to say. There's no better way than to learn it from an industrial perspective. Anyway, so you'll find some great stuff there over the next couple of weeks, and with that, just so that should be released here at the end of next week. Also, be on the lookout for a quiz that's going to be coming up. I think with that, that quiz is going to be our final quiz. We won't have any more quizzes after this week. You'll be focused on your research paper at this point, your modeling and simulation final project paper. So that's all I've got, and thank you for sticking around with me for the lecture. I'm gonna switch on over to the lab.